In this problem, we're told about a hot air balloon that's going up in the air, and we drop a package off the side as the hot air balloon rises. And we're looking at what the behavior of that object looks like as the balloon continues to go up. So we've got some sort of balloon, and there's some sort of block over the side. The balloon is going upwards. At some point, we are going to detach this package. So the package comes off, and we can imagine what will happen is, if the balloon is rising, the package is going to continue to rise for a little bit, but gravity is going to take over. And as gravity starts to set in, the balloon continues to go upwards. The package will continue up a little bit and then fall back down to the ground. That's the behavior that we're trying to find here, where we can imagine the direction of the package will be to continue upward and then fall back down until it hits the ground. So, as far as calculating that, we see that this is a situation where the package is going to be dropped over the side and it's going to fall to the ground. If that's the case, then that package is falling due to gravity, and gravity gives us an acceleration in the y direction of negative 9.8 meters per second squared. That's a constant amount, so that means that we can use our kinematic equations here to represent the motion of this package. Using the kinematic equations, we have the variables. We have the initial velocity of the object, the final velocity, the acceleration, the displacement, and the time elapsed. In this situation, we're told that the hot air balloon is ascending at a rate of 12 meters per second when this acceleration due to gravity begins. So what that means is that at that point in time, when the box is dropped, it's going to be moving with the hot air balloon. And if this is the beginning of its acceleration due to gravity, then its initial velocity is going to be 12 meters per second, and it's positive because it's going upward. We know that it's falling due to gravity, so we know its acceleration will be negative 9.81 meters per second. And we're told that the hot air balloon is 80 meters above the ground when it is when the box is dropped. So that tells us that it's if it's dropped over the side, if it's 80 meters above the ground and it's going to fall all the way down to the ground, then its displacement has to be negative 80 meters because it's ending up 80 meters below where it initially was. So what we see here is that we have 3 of our kinematic variables, which is good. We said that the kinematic equations have 5 total variables. Each equation has 4 variables in it. So if we have 3 kinematic variables, we can use those 3 to find a 4th value. The first thing we're asked is, how long does the package take to reach the ground? How long is a question of time. So that means we're interested in time. We want the equation that has time, but we don't know anything about the final velocity, the velocity at the end of this acceleration. So we want the equation that does not have the final velocity. That equation is this one. Here we have negative 80 meters is equal to 12t plus 1/2 times a negative 9.8 t squared. This is a quadratic equation, so we can rewrite it into terms that are easier for us to use. When we solve this differential equation, we find that t would be -3 or 5.45 seconds. Since we're talking about the time starting at time equals 0, position starting out at a position 0, it doesn't make any sense for us to have a negative time, and thus the solution has to be 5.45 seconds. That's the only one that makes sense for us. When we're interested in the speed at which the box hits the ground, we now have 4 of the 5 kinematic equations because we found time, so we found the 4th one. So technically we could use any kinematic equation now to find the final velocity. However, a good rule of thumb is to remember the ones that you were given and use those values, because those values usually come out a little bit better. If we were to use the time, we already have rounded that a little bit, and so if we plug that back into another equation, we're just going to end up with more rounding errors showing up in our calculations. So if we want to go back to using initial velocity, acceleration, and displacement to find the change in the final velocity, we have an equation that relates all of those. This is our equation that has the final velocity but doesn't have the time, which is one of the values that we just found, and thus is a little bit less correct due to our rounding. We can plug in the values that we know. We want to be careful to use the correct signs of our values. So negative 9.8 when necessary, negative 80 meters when necessary. And from here, we can find our velocity. We find that the final velocity is 41.4 meters per second. In fact, because we're taking a square root, the answer should be plus or minus 41.4 meters per second, because because if you're taking the square root of a number, you don't know which one is correct. However, from the context of the question, that we're moving upwards, we drop the box, it travels upward with us a little bit, and then falls back down to the ground. Its velocity at the end of its flight, when it's hitting the ground, is going to be downward, and thus that means we need a negative velocity in that case, just to show us that the velocity is a downward falling. The last part of the problem to sketch the position, the velocity, and the acceleration. To show the position as a function of time, we said that initially we are at 80 meters, that once we let go of the box, it's going to continue to travel upwards with us for a little bit, and then it's going to fall back down to the ground if we assume that y equals 0 is the ground. This is parabolic motion, and that makes sense because our equation tells us that the position has to be parabolic in nature due to that t-squared term. If we look at the velocity as a function of time, we know that the velocity is initially 12. It's initially going upward. However, we said that the block is going to continue upward for a little bit. It'll hit the top of the arc. At that point, it'll be temporarily motionless, and then it will begin to speed up downwards. As it's heading downwards, it's falling, its velocity is a negative amount. And thus, the graph for our velocity begins at 12 meters per second upwards, but as time goes on, that velocity is less and less as gravity slows it down. Velocity becomes 0 for an instant when the motion stops at the top of its arc, and then that velocity will continue getting larger and larger as a negative number as the box accelerates downward. And finally, if we look at the acceleration versus time, the acceleration here is due to gravity. Gravity is a constant amount, constant negative 9.8, and so the gravity is a constant amount as well.